Hi everybody, video note 7.1. We're going to be doing these things, so take a look. Make sure you read chapter 10 and 14. You'll get all the information for this unit, including this video. So, kinetic molecular theory is a pretty simple theory, but it helps us explain a lot of things. And so what does the theory do? Explain. So the two main points are that all matter is made up of tiny particles, and those particles are in constant motion. Okay. So, oh look, tiny particles, kind of like all matter with the lasers. And then King Juliet's favorite thing, I like to move it, move it. Okay. Anyway, so if all things are made up of tiny particles in constant motion, then that means solids, liquids, and gases are made up of tiny particles in constant motion. So, solids, how are those particles in constant motion? Well, they're mostly vibrational motion, and those are condensed particles. So they're close together, but they're always moving vibrationally. Liquids, they can roll over each other, so they have some rotational motion, and they're vibrating, and a little bit of translational motion as they can go between, spaces a little bit. Gases on liquids are also condensed, but gases are uncondensed. And they have mostly translational motion because they're moving in straight lines in different directions. And they're still rotating and they're still vibrating, but they have a lot of motion and they move all over, ignoring each other. So, why are solids, liquids, and gases? Well, attractive forces between them make them solid, liquid, and gases. So the stronger the forces are, the more solid they are. And then forces that are sort of strong but not as strong will make liquids. And then gases, the forces between particles are non-existent. Right? And so things could be at different states of matter all at the same temperature. So look around the room right now, see something solid, see something liquid, see something gas or know there's gas there. All right, it's all about forces. So energy that we use to describe matter is matter has potential energy and kinetic energy. So potential energy is energy of position that's stored, and we talk about bonds or attractive forces and distance between particles for this. Kinetic energy is energy of motion. So we talk about moving particles and we talk about kinetic energy. Oh, and I just mentioned these kinds of energy. So make sure those are all kinetic because they're all waste things. So now we can talk about solids, liquids, and gases, but those things can change into each other. A solid can turn into a liquid called melting. So here's some vocab words for different phase changes, and here's the actual changes those phase that happen during those phase changes. A gas turning to a solid is called deposition. These are the ones you might not be used to because they skip a phase. But these four you should know already. And just make sure you still do. Okay? So, boiling and evaporation are two different things. Sometimes people use those words interchangeably. But evaporation is something when a liquid turns into a gas where at the surface of the liquid. Actually, it could actually turn directly into a gas from a solid too. And then the temperature, any temperature this could happen at, in all temperatures. Okay, so things are evaporating off the surface of a liquid at any temperature, right? But it's just the molecules at the surface that get enough energy to become a gas. Boiling, boiling happens anywhere in a liquid. So you can have liquid down here, liquid molecules down here that turn into a gas. And so then what are you going to see? You're going to see bubbles, and those bubbles are going to escape. And what's in that bubble is a gas. The temperature is the boiling point temperature of the substance. Okay. Right. So some people don't think about it. They think, oh, it's so hot, it's evaporating. Well, the particles have enough energy to turn into a gas. But actually, it's a cooling process because when those particles with the most energy leave, everything else is cooler because they take their heat with them, right? So a way to think about it is like, oh, hey, there's a dance, and there's 3,000 people in the, or 4,000 people in the gym. Wow, that's crowded, right? If 1,000 people leave, and out of, well, okay, let's just say 3,000. if the hottest people leave, then everybody else is cooler. So there. Look at those dancers. All right. So heat versus temperature. Are they the same thing? No, they're very different. But it's not an easy thing to um, understand. So what I'd like you to think about is that heat is transferred energy, right? Energy that goes from hot objects to cold objects. So heat is transferred energy, and we measure it in calories or joules. And you can't directly measure heat. There's no heat measure, but we can detect temperature changes, and then based on the substance and etc., we can figure out how much heat gets transferred. Okay. Temperature is the average kinetic energy of the particles due to their motion. And there's a formula for it. We're not going to apply it very often, but you will definitely do that in physics. What we use to measure temperature is degrees Celsius, degrees Fahrenheit, or Kelvin. Kelvin doesn't need a degree site because that's the absolute temperature scale, and the bottom of that is 0. But you can go below 0 on Celsius or Fahrenheit. We're going to most often use Celsius. Okay. And we use a thermometer to measure heat. I'm sorry, I said heat. Come on, Harbin. We use a thermometer to measure temperature. You can't measure heat directly. You can measure changes in temperature due to heat transfer. So heat is energy transferred from hotter objects to colder objects. So let's talk about what has more energy, a drop of boiling water or a snowman sculpture of a bunny. Well, all of the particles in here are in constant motion, so they have some heat energy due to motion, right? All of those particles have stored energy, so they have potential energy. So if you add those all up, they probably have more energy than this one hot drop of water, okay? So we're going to be able to detect and measure data and then calculate the amount of heat transfer. Woohoo, yay us. So heat, what does heat do? It flows from hot to cold. So hotter particles move faster. So they come into contact with colder particles and they transfer their heat and cause the colder particles to start to move faster. Okay. So if things are at the same temperature, there's no heat transfer. If things something at a warm temperature is going to transfer to cool, something at a high temperature is going to transfer to a cold temperature. So the heat will be transferred and the temperature will change. Right? You know what happens when you touch an ice cube, right? You're holding it, you feel the heat transfer, right? Now, it's from your hand into the ice cube. That's your feeling, heat transfer. So we can quantify this kind of stuff with what we call a heating curve. And there's a heating curve that can be created for every pure substance. Okay, so elements and compounds have heating curves for them, right? And on the heating curve, the flat part is where a phase change is happening. Okay, so this would be the melting point of a substance, and then over here we have the boiling point of a substance. So these are temperatures on this axis, and notice what happens during a phase change. You have two phases. You have the one that starts as and the one it's going to, but notice what happens to the temperature. Look at this line compared to this line, and think about why it would take longer to, so this is for the same mass of a substance. So say this is 50 grams of a substance. It would start out solid over here, and then the solid would turn into a liquid. It would be liquid here. Liquid would turn into a gas, and over here would be all gas. Why would it take longer for a liquid to turn into a gas, even though it's 50 grams, than it would for a solid to turn into a liquid? Hey, that was a heating curve. This is a cooling curve. What's the difference? The difference is here you're taking away heat energy, and so the temperature is going down. Adding heat energy to I said the temperature is going up in some places, so energy is increasing, heat's being added. Here, energy is decreasing and heat's being removed. Not everywhere is temperature changing. It's only changing on these slanting parts. And temperature stays constant on the flat parts, but heat is changing the whole time. Okay, so we're going to talk about this in class, and we'll answer this question. But you can see it on this heating curve. If you're going this way, you're adding heat. If you're going this way, you're taking away the heat. If you're going right, you're adding heat. If you're going left, you're taking away heat. And then there's a diagram of the particles to kind of give you an idea of what's going on. So we'll keep talking about it. we have to be able to analyze data and sketch a graph for a substance. So, oh look, it's Moltato. There's Moltato. There's nose, there's eye, all these things. Okay, so Moltato, we're pretending Moltato is a pure substance, right? And we're heating Moltato from 120 degrees Celsius to 200 degrees Celsius. So anytime you're drawing a heating curve, this is make a heating curve. So sketch a graph. It's just a sketch. You put the temperatures given in the problem. So we have 120 degrees Celsius. I'll put that lower. And 200 degrees Celsius. I'll put that a little higher because it's a higher temperature. Okay. Here's information that has to be given. Right? You have to know what Moltato's melting point and boiling point are. Okay. But our problem only deals with this range. So that's only the range that we need on a graph because it's the range in our problem. All right, now I look to see in this temperature range, is Moltato going to go through a change? So at 210 is above our range, so not going to happen. So we don't have to worry about that one. But Moltato should melt at 155 degrees. So because that's in between the two temperatures I already have on my graph, my range I'm talking about, I have to put it on my graph. And so Moltato is going to heat up, temperature changing until it reaches 155 degrees Celsius, and then it's going to flatline and Moltato is going to melt, and then Moltato will be a liquid up into 200 degrees. So this is going to be solid there. Moltato is solid below its melting point. Here's where Moltato is going to turn from solid to a liquid. And then here, Moltato will be a liquid the whole time. Okay? So this is how you sketch a graph. So you read the temperatures given in the problem, put them on the graph, check the melting and boiling point, and if it's in between the range given, you have to add it. Remember to flat line at a phase change. Okay, so we'll be able to calculate the heat changes during phase changes because those are the flat parts. So flat part phase change. There's an equation we use. So to calculate the heat, we're going to need the mass of the substance and know something about the substance. So you need to know Q is heat, and that's usually what we're looking for. We need to know M is mass. How much does the substance, how much mass does it have? Because that's going to, if it's a really big substance, it's going to take a lot of heat to change its phase, right? And then delta H is the change, the heat of phase change. Heat of phase change. All right. Now, you don't have to memorize that. You'll be able to look it up, but it is going to be units. So Q is heat, and that's going to be calories or joules. M is mass, and that's going to be usually in grams. It could be kilograms, whatever. This is the heat of the phase change. And that's going to be in calories, per gram or joules per gram. So it depends on what states are changing. So is it solid going to liquid? Is it liquid going to gas? Is it gas going back to liquid? Right. So we have to know what states are changing. So use the delta H depends on this. And can be looked up. And can be looked up. Right. What's happening here? Oh, solid's turning liquid. All right. Now, that was for the flat parts on the graph. Now, every graph has some slanted parts. Well, not every one of them, but a graph could have a slanted part. And so we're going to need a different equation there because we're going to need to know that on a slanted part, the temperature is changing. You have to know how much it changes. So you need to know that the Q is the heat, again, and that's calories or joules. M is the mass, and that's in grams. C is called specific heats of substance. So it depends. Am I heating up Moltato? Am I heating up okay, so specific heat depends on your substance, right? Depends on substance. So it depends on what substance you're looking at. Is it iron? Is it copper? Is it ethanol? Is it H2O? Right? And then This is the change in temp. So there's going to be two temperatures on this lamp, right? So we have to subtract them. The change in temperature, and that's in degrees Celsius. So you need to know a lot of stuff. All right, so different states of matter have different energies. We talk about that. Temperature is average kinetic energy, no matter what state it's in. And states have different potential energy based on their bonds or attractive forces. So usually potential energy, so solids have the lowest potential because their particles are close together, right? So there's not much distance between them. Liquids have a medium potential because their particles are a little bit further apart, but they're still pretty close, right? Gases have highest potential because look at the distance between them. Okay? Like this is a big distance, so it's bigger. Think about if you're standing on the floor. Oh, look, you're standing on the floor, or you are. Look at this ladder. That's a ladder, right? Or you climbed up the ladder. And you're standing on the ladder. All right. Because of your distance from the ground, you have a higher potential. So the distance between particles in a gas would give them higher potential. Okay. So I want you to think about this. We'll talk about it in class. So you're like, what are you going to say for these? And then here is a ton of vocabulary. So I'd like you to look at it, see if you know it, jot it down, make sure you write it, draw pictures about it to help understand, right? So you say write it, draw it, do it. So to review, make sure you know that intermolecular forces and bonding affect states of matter. So those are the attractions. Strength of attractions. Strongest forces are solid, weakest forces are gas. Kinetic is motion. Potential is position and distance apart. Evaporation is cooling. Heat and temperature are not the same. All right. Know which way energy flows and know what happens at a phase change. Temperature is constant. And if temperature is changing, kinetic energy is changing. There'll be a slant on a graph. All right. It's a lot of talking, not a lot of math in this one. Get that vocab down. Peace out.